Welcome to this lecture in our course block on multi-access solutions. Today we take a look at two of the key concepts that needs to be considered when designing a multipath protocol: reliable transfer and congestion control. My name is Anna Brunström, professor in computer science at Karlstad University. So in this lecture we will first quickly recap what distinguishes a multipath transport protocol from single path communication. And we will then move on to the two key topics of today's lecture: reliable transfer, how do we identify the data sent over the connection and how do we manage retransmissions, and congestion control, introducing the basics of congestion control and then looking at resource pooling and coupled congestion control, which are two key concepts for congestion control in a multipath context. First, remind ourselves what is needed for multipath transport. So we do have to consider the same key mechanisms as needed also in single path communication: how to set up our connections and how to manage the data transfer. But in contrast to single path communication, we also have to consider in these mechanisms that we now have multiple paths available for the communication, as illustrated in the figure. So in previous lectures, we have introduced the key concepts that needs to be considered when designing a multipath transport protocol. We have to deal with the connection management and how we manage the different paths. And related to the data transfer, we have to deal with the packet scheduling, how to ensure reliability and managing appropriate congestion control. And in this lecture, we will take a closer look at the last two concepts, starting with reliable transfer. So in order to ensure a reliable transfer, we need to consider how to identify our data, how to manage the sequence number space, and how to recover data once it is lost. To provide a reliable data transfer, this requires some form of sequence numbers and acknowledgement mechanism to keep track of what data has been delivered from the sender to the receiver. And if we now do this in a multipath context, then there are a few different ways we can manage this sequence number space. So we may, for instance, have a sequence number space only on the connection level, one single sequence number space that is used across subflows. The other alternative is to have a sequence number space both at the connection level and at the subflow level. So each subflow has its own sequence number space, and then we connect it to a sequence number space on the connection level. And the choice here has different implications. If we make a sequence number space on both the subflow and connection level, it is easy to identify which packets has been delivered on each subflow. If we instead have a single sequence number space for the connection, we typically have to then keep track of where we send the packets so that we make sure that we can account for what has been delivered on different paths in a good way. So as an example, let us see how the sequence number space is managed in MPTCP. For MPTCP, the subflows look as normal TCP flows. And we don't have a choice here for how we manage the sequence number space if we want our traffic to make it through the internet and the many middle boxes that may be passing through along the path, because these middle boxes will expect TCP to have the bytes in sequence. So in MPTCP, we have to use the normal TCP sequence numbers on the subflow level, and then we have a second sequence number space on the connection level. And we then need to map these connection level sequence number down to the subflow level. And this data sequence mapping is fixed. And in MPTCP, in order to deal with the many middle boxes that may be on the path, we have to also consider how to do this mapping in an appropriate way. And the way it is done in MPTCP is that the sequence number space on the connection level indicates the offset into the data stream on the subflow relative to the initial sequence number. And using the relative offset is important here, because if you map it to the actual sequence number that is used when you start up the connection, you may have middle boxes on the path that modify this sequence number and thereby breaks the mapping between the connection level and the subflow level. So the design for MPTCP in how to manage the sequence number space is very much influenced by its need to go through all the different middle boxes that you may encounter on an internet path. So if we now have a sequence number space, then we can identify our data. And if data is lost, then we will have to retransmit this data. And here we also have multiple options available if we are operating in a multipath context. So we may, for instance, choose to retransmit the data on the same subflow where the original packet was sent. We could also choose to retransmit our data on an alternate subflow, thinking that maybe it's better to pick another subflow that is more reliable. Or we can use some combination of the two alternatives. For instance, retransmitting the data on both of the subflows, both the original subflow, where the data was originally sent, and on an alternate subflow. And if we look at how MPTCP handles retransmissions, it always retransmits the data on the same subflow where the original segment was sent. And this is again tied to the TCP semantics. TCP is a reliable byte stream, so as we are using TCP connections as our underlying subflows, we have to retransmit our data on the original subflow in order for TCP to make progress. However, MPTCP also may retransmit a packet on an alternate subflow. And the way MPTCP decides is that if a timeout occurs, then it will retransmit the segment also on an alternate subflow. So on multiple subflows in this case, both on the original subflow and on an additional subflow that it has available. And this, of course, is because the timeout is an indication that we have some severe problems on the path. On the other hand, if we recover and detect a packet loss through a fast retransmission, then we will only retransmit it on the TCP subflow, the original subflow. And one thing to keep in mind here is that in the end, the loss recovery must always be ensured at the multipath level, irrespective of which protocol we are talking about here. Because of course, if we don't ensure it on the multipath level, we will lose the ability to provide reliability also in the case of path failures. And this is of course one of the main advantages of multipath communication, that even if we have a path break, we will be able to maintain reliability if we have alternative paths available. So we have to maintain the data so that it's available on the multipath level and can be retransmitted on the multipath level if needed. So let us move on to the second key concept considered in this lecture, namely congestion control. So the congestion control is responsible for managing the amount of data that you can send into the network at a particular point in time, in order to not have a too high rate. And now we are in a multipath context, so we of course have to consider how congestion control is managed across our multiple paths. Before we get into the details of the multipath congestion control, let us briefly recall the basics around congestion control. So congestion occurs when you send something into the network faster than it can be delivered. So in the figure below, we have 3 paths going into a network buffer, each of them sending at 100 megabit per second, and we have an outgoing link of 100 megabit per second. So of course, in this example, if we keep sending at this rate over all the 3 incoming paths, you will have an overflow of this buffer. The network element cannot keep up with the incoming rate. It's not able to deliver the same amount of data out. So this will lead to congestion. So if congestion occurs in the network and packets are dropped, what happens at the transport layer? Well, if we are providing a reliable transport, then the transport layer will retransmit the lost packets. And if we have a severe congestion where many packets are lost, all the senders will continuously retransmit these packets. And if this is done without taking care of the congestion, then we will may end up in what is called congestion collapse. And this is a state where no real useful data is passed through the network because you keep getting a lot of retransmissions and the packets are lost over and over. And this was a phenomena that was first discovered in the 80s at the Ford Aerospace. And of course, the concept of congestion control was then developed to try and deal with this problem. So the goal of congestion control is to remedy and avoid congested scenarios. So the transport protocols today are all equipped with congestion control mechanisms. And the dominant transport protocol on the internet, TCP, Transmission Control Protocol, has been very successful, and it's clear that one of the reasons for this is its efficient congestion control mechanisms, and that is how it has been able to manage the many flows that may go over the network. And of course, the very early and first work on this area that introduced and started the work on congestion control was the work by van Jacobson, presented at SIGCOM in the Congestion Avoidance and Control paper. And over the years, there has been many modifications and improvements to the congestion control, but the basic principles of the slow start and congestion avoidance still remains. So let us then move into the multipath context. So what is special about multipath congestion control? Well, if you have multiple paths to consider, congestion control gets slightly more tricky. So it would of course be possible to just run a regular single path congestion control of each of your individual subflows. The problem with this is that it will not be fair to other flows in the network. If your congestion control runs separately on each individual subflow, it will be much more aggressive than any other single path flow that may be competing with you over the same path. And this is therefore not the solution that can be used in general over the internet. So this brings us to the principle of resource pooling. So resource pooling aims to make use of the resources of a network like it was a single pooled resource. And this is a general principle that can be applied not only to multipath congestion control, but also in other contexts. And of course, if we can use a pooled resource, this provides increased robustness, and it can also then handle larger bursts that may appear because you pool the resources that are available and you can utilize them more efficiently. So we have an illustration of this in the figure in the slide. So consider a single path resource and you have two different flows going into this path. If you now have multiple paths available, you would like to use it as if it was a single path and that you use the combined bandwidth available over these two paths as a single resource. And you can see in the figure that the green flow here would not be able to be supported by a single path, but by both of the paths, this burst is available. And we can also see that the utilization is improved here, because if we only could use one path each for the red and the green, we would waste some of the resources. But here we can pool the resources and the green one can take advantage of something that is free on the bottom path, and the red one at a later point in time takes advantage of what is available on the upper path. So the resource pooling principle is a general principle that can be applied also in other contexts. But in the context of multipath transport, the resource pooling principle then allows multiple paths to be treated as a single pooled resource. And the goal here is to be both fair to single path flows and improve performance and robustness when you use multiple paths. And the benefit here, if you use the resource pooling principle and you are a multipath transport, is that you can move traffic away from congested links and then leave the resources on that link available for other flows that may not have other capacity available. So protocols like MPTCP use congestion controllers that builds on the resource pooling principle. And a congestion controller that builds on this principle uses a coupled congestion control algorithm. And the coupled congestion control algorithm, what we mean by that is that the congestion control algorithms operating on the individual subflows are coupled. So you don't increase your congestion window on the two paths independently. Instead, the increase is linked to each other and you increase it so that you treat the paths as a pooled resource. And this is something that is required if you want to use your multipath protocol as a general operation on the internet. However, there may of course be situations where it can be both beneficial and appropriate to treat each subflow separately. So if you have no shared bottlenecks and perhaps you have acquired two uplinks to gain capacity, and there is no shared bottlenecks along the path, then maybe in such a scenario it would be perfectly fine to also use uncoupled congestion control. That is a single independent congestion control on each of the paths. But for general operation on the internet, the coupled congestion control is very important for ensuring stability and fairness to other flows. So to summarize, we have covered two key concepts in this lecture: reliable data transfer and congestion control. And to provide a reliable data transfer, we need to keep track of the data, and we need to make sure that if some data is lost in the network, it has to be retransmitted. And in a multipath context, we then have to decide how to manage our sequence number space to identify the data. Do we have a sequence number space both on the connection level and on the subflow level, or is it enough to just have one on the connection level? And when we have a data loss in the network, what paths do we use for retransmissions? We have also seen that congestion controllers are important to try and control the sending rate into the network to ensure that we avoid a congestion and a massive loss of packets in the network. And when we have congestion control for a multipath transport, then we have to consider the paths as a single resource to be fair to competing traffic. So the coupled congestion control is a key mechanism for multipath transport communication.